Next, I'm going to introduce a new set of functions that are based on exponential functions. And these are called hyperbolic trigonometric functions. So these ones are called hyperbolic trigonometric or hyperbolic trig functions. So the two primary hyperbolic trig functions are the hyperbolic sine and hyperbolic cosine. Hyperbolic sine and cosine. So hyperbolic sine and hyperbolic cosine. So they're denoted sinh of x and cosh of x. So sinh of x is defined as e to the x minus e to the minus x over 2. And cosh of x is equal to e to the x plus e to the minus x over 2. So this is the definition of the two primary hyperbolic trig functions, sinh and cosh. And so basically, sinh and cosh are each linear combinations of exponential functions. By linear combination, I mean it's some constant times e to the x plus some constant times e to the minus x. So that's a linear combination of e to the x and e to the minus x. So today we're going to explore sinh and cosh and discuss some of their properties. Now at first you might say, what on earth does this have to do with sine and cosine? Well, there's a lot of similarities between sinh and cosh, or the sinh and cosh functions and the sine and cosine functions. So hopefully we'll be able to explore some of those similarities today. But for now, just treat this as a definition. So sinh is just the name of a function. Cosh is just the name of a function, and these are specific functions defined in this way. First, we can take a look at what these functions look like. So here's a graph of the sinh and the cosh functions. So cosh is this red curve, and sinh is the blue curve. So there's a few similarities right off the bat between regular sine and cosine. First of all, like cosine, the hyperbolic cosine function has the property that cosh of 0 is equal to 1. So when evaluated at x is equal to 0, it returns the same output as the cosine function. Similarly, sinh of 0 is equal to 0. So the sinh equation, the sinh graph, passes through the origin just like the regular sine graph does. Also, you can look at even and odd. Hyperbolic cosine function is an even function, meaning it's a mirror image about the y-axis, just like cosine is. And then the sinh function is odd, meaning that sinh of minus 1 is the negative of sinh of 1. And you'll also notice that these two functions approach each other as x goes to infinity. They get very, very close. And then as x goes to minus infinity, they approach the opposite of each other. So sinh is approximately the negative of cosh for large negative values of x. The ratio of sinh divided by cosh is called tanh, or T-A-N-H, and the tangent function looks like this. So it's a function with two horizontal asymptotes, one equal to minus 1 and the other horizontal asymptote equal to plus 1. So tanh basically transitions from minus 1 to plus 1 as x goes from minus infinity to plus infinity. So we can define tanh of x as sinh of x over cosh of x. The same way that tangent function is defined as sine of x over cosine of x. Or we can write e to the x minus e to the minus x divided by e to the x plus e to the minus x. So the limit as x goes to infinity, as you can verify, is 1. The limit as x goes to minus infinity is minus 1. So let's start with just looking at the derivatives. So let's start with the derivative of sinh. So the derivative of the sinh function, so the derivative of sinh of x, so d by dx of sinh of x is, well, this is the derivative of e to the x minus e to the minus x over 2. Well, the derivative of e to the x is just e to the x. The derivative of e to the minus x, we start by rewriting it, so minus e to the minus x. Then we multiply by the derivative of the exponent. So the derivative of the exponent is minus 1, so it turns into plus. And then the 1 over 2 is just a constant, so that just stays along. So we'll notice that the derivative of cosh, or derivative of sinh, is just equal to the cosh function. You can also show that the derivative of cosh is equal to sinh. Right? So basically, when we look at the cosh function, this minus sign comes down, and then it turns into the sinh function. So it's similar, but here's a little bit of a difference. So derivative of sine is cosine, so we'll see that coming up, but we've already seen it in the basic derivative rules, how the derivative of sine is cosine. The derivative of cosine is negative sine. So the difference here is that the derivative of sinh is cosh, and the derivative of cosh is sinh. So instead of the second derivative being the negative of the original, right? So if you have sine of x, the derivative is cosine of x, and the second derivative of sine of x is negative sine of x. Cosine of x, its derivative is negative sine of x, so therefore the second derivative of cosine of x is negative cosine of x. So you'll notice with the basic trig functions, the second derivative is always the negative of the original, whereas with the hyperbolic trig functions, the second derivative is equal to the original. The second derivative of sinh of x is equal to sinh of x. The second derivative of cosh of x is equal to cosh of x. So that's one analog between regular trig functions and the hyperbolic trig functions. There's another one, another analog. So sine and cosine satisfy the relationship that cosine squared of x plus sine squared of x is equal to 1. Now, the hyperbolic sine and cosine satisfy something similar. Cosh squared of x minus sinh squared of x is equal to 1. So instead of adding them together, when you subtract them, you get 1. And we can see this, so let's prove this fact. So cosh squared minus sinh squared is equal to 1. So, well, cosh squared of x, well, we just have to square this equation right there. So it's going to be e to the x plus e to the minus x over 2 squared. Well, when we square this, we get e to the x squared, so that's e to the 2x, plus 2 e to the x, e to the minus x. Now, e to the x times e to the minus x is just equal to 1 because e to the minus x is the reciprocal of e to the x. So we just get plus 2 and then plus e to the minus 2x. So e to the minus 2x is e to the minus x squared. So we get e to the x plus 2 plus e to the minus 2x over 4. And similarly, sinh squared of x is going to be e to the 2x minus 2 plus e to the minus 2x all over 4. So that just comes by expanding this one. We get this one squared plus this one squared and then minus this times this. So we get a minus 2 there. Minus 2 times this times this. Now when I subtract, when I do cosh squared minus sinh squared, notice what happens. This will cancel with that. 1/4 e to the 2x minus 1/4 e to the 2x. 1/4 e to the minus 2x minus 1/4 e to the minus 2x. So this cancels with this cancels with this. Since I'm subtracting the second one, 2 over 4 is 1/2 minus another 2 over 4. So we get 1/2 minus negative 1/2, which is just equal to 1. So therefore, cosh squared minus sinh squared is equal to 1. So those are some of the basic properties of sinh, cosh, and a brief introduction to tanh. Final point of comparison between regular sine and cosine and the hyperbolic ones is as follows. Let's clear some space. Actually, let's keep that one there. So before we mentioned how cosine squared of x plus sine squared of x is equal to 1. So in particular, this describes the unit circle. So on the unit circle, I have an angle theta, and then the position is going to be cosine of theta is x, and sine of theta is y. So we have x is equal to cosine of theta, y is equal to sine of theta. So x squared plus y squared is going to be cosine squared of theta plus sine squared of theta, and that's just equal to 1. And we recognize that x squared plus y squared equals 1 is just the basic equation for a unit circle centered at the origin. So this relationship cosine squared theta plus sine squared theta is equal to 1 is really just a statement of the fact that the point x equals cosine theta, y equals sine theta travel around a unit circle. Now you can say something similar with this one. So instead, let's say that we have x is equal to cosh of theta, so hyperbolic cosine of theta, y is equal to hyperbolic sine of theta. And because of this relationship, we know that x squared minus y squared is equal to 1. So this is an example of a parametric curve, and we're going to look at parametric curves in more detail later on, but this is a nice introduction. So basically, theta takes the place of a parameter. So as you vary theta, you get different points. And we recognize this equation as the equation for a hyperbola. So if x is equal to 0, I don't think there are any solutions. I think this parabola opens up this way. So this is just a parameterization of this parabola that opens up to the sides. So whereas sine and cosine can be used to parameterize a circle, the hyperbolic trig functions can be used to parameterize a hyperbola. So that's another analog between regular sine and cosine and the hyperbolic trig functions. So hyperbolic trig functions are also useful in differential equations and in certain applications because of the nice properties that cosh of 0, I mentioned this earlier, that cosh of 0 is equal to 1, and then sinh of 0 is equal to 0. Right? So basically, it's easy to, when you have a differential equation, you have a choice. Given these functions cosh and sinh, sometimes you have solutions to a differential equation that might look like this: a e to the x plus b e to the minus x. So you have f of x like this. And then you have to choose a and b so that f of 0 is some given value and f prime of 0 is some given value. Well, f of 0 is going to be a plus b, and then f prime of 0 will be a minus b. So you get a plus b equals something, a minus b equals something, and you can do it that way. But on the other hand, you can equivalently say that f of x is equal to c cosh of x plus d sinh of x. Well, in this case, f of 0 is just equal to c, and f prime of 0 is just equal to d. So it's a lot easier to choose the constants in these sorts of applications given the initial data. So you have some given f of 0 and some given f prime of 0. And you have to choose the a and b, or you have to choose the c and d to satisfy that initial data. So oftentimes you get it's a little bit of a simplification using sinh and cosh. And so they're really just combinations of exponential functions that have special properties that are worthwhile knowing about.